Good morning everyone. I am Vinay Raj, working as Assistant Professor in Department of Civil Engineering in MIT Mysore. Today I am going to start Module 2, and that is Equilibrium of Forces and Friction. So in Module 2 there are two parts. The first part is Equilibrium of Forces and the second part is the friction. So from today I am going to start the first part, and that is equilibrium of forces. In this, first we have to understand some concept, and the first concept is equilibrium. We have to understand what is equilibrium means. Then we have to understand what is equilibriant or equilibriant force. Then we have to understand equilibriant moment. Then equilibrium conditions. At last we have to understand the Lami's theorem. To start with, let us understand what is the meaning of the word equilibrium, for which I am going to consider an example, right? Let me consider a body whose area will be equal to A. If I apply a force on this body and the magnitude of the force is F1, see, this is called as a system. In this system, there is a body. On that body we have applied a force F1, and this is called as a system, right? When I apply a force F1 on the body, it is common sense the body will tend to move, or it will try to move in the direction of the applied force. It is a common sense, right? Whenever you apply a force on the body tends to move, or the body is going to move in the direction of the applied force, and that is called as the resultant of this system. In this system, there is a body and we have applied the force. Due to the application of the force, there is one resultant, and that resultant is in the form of motion of the body. And the motion of the body will be always in the direction of the applied force, and this is the resultant R of this particular system. Even after applying a force on the body, if the body doesn't move, still if the body is in static position, still the body if it is in rest position, you can say the body is in equilibrium. The whole system is in equilibrium, because even after applying a force on the body is not moving. The body is in static position. So we can say the body is in equilibrium. The complete system is in equilibrium. When the system is in equilibrium, the resultant of the whole system will be equal to 0. This is very, very important, right? If you want to say the body is in equilibrium, if you want to say the complete system is in equilibrium, the system resultant should be equal to 0. It is a very, very simple concept. Understood? Equilibrium is nothing but even after applying a force on the body, if the body doesn't move, if the body still it is in state of rest, then you can say the body is in equilibrium. And always when the system is in equilibrium, the resultant will be equal to 0. Understood? Right? So let us move to the next concept, and that is called as equilibriant or equilibriant force. See, in order to explain this, I am going to consider the same example. So in which there is a body and we have applied a force on the body, and there is a resultant, and that resultant is in the form of motion of the body. The body is moving in the direction of the applied force, right? Say, if you want to bring the moving body in state of rest, if you want to stop the motion of the body, what we have to do? This is the same example I am going to consider. This is the body. This is the applied force F1. If you want to bring the resultant is equal to 0, then you have to apply one more force of same magnitude but in opposite direction. Now the resultant of this system is 0. Now this system is in equilibrium. To bring this system to equilibrium, this force is responsible. That is the reason why this force is called as equilibriant force. This force is responsible to keep the body or to keep the system in equilibrium. That is the reason why it is called as equilibriant force. That's it. Next, let us understand equilibriant moment, right? To explain this, I am going to consider a body in which number of forces is acting on the body. Totally there are 3 forces, F1, F2 and F3, and this is one system. So in this system there is a body and 3 forces is acting on the body, right? And there will be one resultant, right? Now for this particular system, the resultant is in the form of rotation of the body. That means the body is rotating in the same position and that rotation can be represented by the moment. In any system, the resultant may be in different forms. In the first example, the resultant was the body was moving in the direction of the applied force. In the second example, the resultant is in the form of rotation. That means I am going to consider the same body. Due to the application of these 3 forces, the resultant is in the form of rotation. That means the body will be rotating and that rotation will be represented by M, that is called as moment. The rotation can be represented as moment, and this is the resultant of this system. Say if you want to bring this system in equilibrium, then you have to stop the rotating of the object. Very simple, right? That means I need to apply one more momentum of same magnitude but in opposite direction. Therefore, this moment will see that the body will come to equilibrium position. The body will stop rotating. That is the reason why this M is called as equilibriant moment. Very, very simple. Understood? M, that moment is responsible to bring this body to the equilibrium. This M is responsible to stop the rotating of the object. That is the reason why it is called as equilibriant moment. Understood? So we got to know what is equilibrium, then equilibriant force and equilibriant moment. The next very important concept, that is equilibrium condition. So using these conditions we are going to solve the problems, right? So it is very important. What is equilibrium condition? See, whenever you consider any system, if you consider this particular system, if you want to say this system is in equilibrium, then it has to satisfy 3 equilibrium conditions. Understood? If you want to say one system is in equilibrium, then that system should satisfy 3 conditions. Let us see what are those conditions. And those conditions are called as equilibrium conditions. See, there are 3 equilibrium conditions. The first one is summation of fx is equal to 0, summation of fy is equal to 0 and summation of m is equal to 0. These three conditions are called as equilibrium conditions, and these conditions are used in order to solve the problems. Right? Okay. Say, if this system, if I consider this system is in equilibrium, then this system should satisfy these three conditions. The first condition is known as summation of fx is equal to 0. That means in this particular system, summation of all horizontal forces should be equal to 0. In this system, summation of all vertical forces should be equal to 0. In this system, summation of all moment is equal to 0. Then you can say this system is in equilibrium. The same thing is applied to this system also. If you want to say this system is in equilibrium, then this system should satisfy these three conditions. That means in this system, all the horizontal forces, summation of all the horizontal forces should be equal to 0. Summation of all the vertical forces should be equal to 0, and summation of all the movement in this particular system should be equal to 0. Then you can say even that system is in equilibrium. Understood? I hope you have understood the equilibrium conditions. So in equilibrium conditions, there are two things. The first one is called as equilibrium condition for coplanar concurrent force system. Second one is equilibrium condition for coplanar non-concurrent force system. There are two things, right? Let us understand what it is. What is the meaning of concurrent forces? Concurrent forces means the forces, if it is passing from the same point, then those forces are called as the concurrent forces. And if all the forces is lying in the same plane, then you can say it as a coplanar concurrent forces, right? So these three forces are concurrent. These three forces are concurrent, and also it is lying in the same plane. So that is the reason why it can called as coplanar concurrent force system. Right? If you want to say this coplanar concurrent force system is in equilibrium, then it has to satisfy only two equilibrium conditions out of these three. For coplanar concurrent force system, the equilibrium condition to be satisfied is only two, that is summation of fx is equal to 0 and summation of fy is equal to 0. Summation of m is equal to 0 will not come under coplanar concurrent force system. Understood? If the problem is coplanar concurrent force system, then you can use only two equilibrium conditions to solve the problems. That is the important point, right? Next, the next one, it is equilibrium condition for coplanar non-concurrent force system. Non-concurrent is nothing but if all the forces is not passing from the same point, then you can say it as a non-concurrent force system, right? For that, this is F1, this is F2, this is F3, and this is F4, and all the four forces is not passing from the same point. Therefore you can say this is non-concurrent systems, right? And if these forces lie in the same plane, then you can say it as coplanar non-concurrent force system. If you want to say this coplanar non-concurrent force system is in equilibrium, then that system should satisfy all the three equilibrium conditions, right? That is, for this it has to satisfy summation of fx is equal to 0, summation of fy is equal to 0, summation of m is equal to 0. That means for coplanar non-concurrent force system problem, you have to use all these three conditions in order to solve the problem. Understood? Right? So we discussed about equilibrium, then equilibriant force, then equilibriant moment, then equilibrium conditions. In that there are two things, right? And at last we have to move for the last topic, and that is Lami's theorem, right? Let us move to the next topic, and that is Lami's theorem. See, Lami's theorem is a very important derivation, and we are going to use this Lami's theorem in order to solve the problem. To solve the problem in equilibrium of forces, we have to use equilibrium conditions or Lami's theorem. Only two things we have to use in order to solve the problem in equilibrium of forces, right? See, Lami's theorem states that if three coplanar concurrent forces are in equilibrium, if three coplanar concurrent forces are in equilibrium, then each force is directly proportional to sine of the angle between the other two forces. This is the statement, and we need to prove this statement now. According to the statement, we have to consider only three forces. According to the statement, the three forces should be concurrent and it should be in equilibrium, right? So let me consider the three concurrent forces first. I am going to consider three forces, and all the three forces are concurrent. So this is F1, this is F2, and this is F3. Let me consider this angle is alpha. Alpha is the angle opposite to F1 and it is in between F2 and F3, right? Let me take this angle is beta, and beta is the angle opposite to F2 and in between F3 and F1. Let this angle be gamma, and gamma is the angle opposite to F3 and in between F1 and F2, and this is how you need to represent the angles. It is very, very important. You should not change the angles in the figure. Okay? Next. So these are the three coplanar concurrent forces, and very important is this system is in equilibrium. When three coplanar concurrent forces are in equilibrium, then these three forces can be represented by the sides of the triangle. That's what I am going to do in the next figure. I am going to represent these three forces in the form of sides of the triangle, right? So this is the first force. I am going to draw the first force here, and this is F1. This is F1. Next, this is F2. I am going to draw this F2 here, and this will be F2. So this is F3. I am going to draw this F3 here, and this will be F3. So three forces are representing the three sides of the triangle, and this is the line of action of F1, line of action of F2, line of action of F3. Now let us place the angles, right? That is, angle alpha is placed in between F2 and F3, right? This is line of action of F2. This is F3. That means alpha should be here. Next, beta is in between F1 and F3. Beta is in between F1 and F3. So this is line of action of F3 and this is F1, and this will be the angle beta. Next, this is gamma in between F1 and F2. Now, this is line of action of F1 and this is F2, and this angle is gamma. Understood? Now, using this alpha, beta and gamma, let us calculate the internal angles. This internal angle will be equal to, see, this is 180 degree. Out of 180 degree, I should subtract alpha to get this internal angle, and this internal angle will be equal to 180 minus alpha. In the same way, this will be equal to 180 minus beta. and in the same way this will be equal to 180 minus gamma. That will complete the triangle. Right? So I have represented the three coplanar concurrent forces by the sides of the triangle, and also I have mentioned all the angles. Right? Next. The next step is, now I need to apply the sine rule for this triangle. What the sine rule states? See here. The sine rule states that if three forces are represented by the three sides of the triangle, then each side is directly proportional to sine angle of the other two sides. Each side will be proportional to sine angle of the other two sides. That means now I need to apply the sine rule for this triangle. Right? Apply sine rule for the triangle. When I apply the sine rule for the triangle, it states that each side is directly proportional to the sine of the angle between the other two forces. That means F1 should be proportional to sine of this angle. F2 should be proportional to sine of this angle. F3 should be proportional to sine of this angle. That's what I am going to write here. That means here F1 is proportional to sine of 180 minus alpha. Next, F2 is proportional to, see, F2 should be proportional to the opposite angle, and it should be the angle between the other two sides. Right? So F2 is proportional to sine of 180 minus beta, and F3 is proportional to sine of 180 minus gamma. So by applying the sine rule, I got three equations. Right? So in these three equations, now I am going to remove the proportionality, and I am going to introduce a constant. Right? That is, F1 is equal to k times of sine 180 minus alpha. Then F2 is equal to sine of 180. That is F2 is equal to k times of sine 180 minus beta. Next, F3 is equal to k times of sine 180 minus gamma. Now, equating these three equations, the constant k will be cancelled, and we know what is sine 180 minus alpha. Sine 180 minus alpha will be equal to sine alpha. We know that, right? Sine 180 minus beta is sine beta. Sine 180 minus gamma is sine gamma. By equating all these three equations, that is, by equating three equations, we get F1, k is a constant, it will be cancelled, and sine 180 minus alpha is equal to sine alpha, and F1 is proportional to sine alpha equals F2 is proportional to sine beta equals F3 is proportional to sine gamma, and thus it proves the Lami's theorem. Very simple, but it is very important. It is examination question. Lami's theorem derivation is an examination question, right? Okay, see what the Lami's theorem states. Three coplanar concurrent force system are in equilibrium. Then each force F1, F2, F3, each force is directly proportional to the sine angle between the other two forces. See, F1 is proportional to sine alpha, and sine alpha is the angle between the other two forces. F2 is proportional to sine beta and F2 is here. F2 is proportional to sine beta and sine beta is the angle between the other two forces. F3 is proportional to sine gamma and sine gamma is the angle between the other two forces, thus proves the statement of the Lami's theorem. Right? Let us move to the next topic, and that topic is called as free body diagram. Even this topic is very important because in order to solve the problems, the first step will be to draw the free body diagram. If you consider any problem in equilibrium of forces, the first step of the problem will be to draw the free body diagram for the system. Right? See, free body diagram is the isolated diagram in which we have to represent the self weight of the body, the reaction and the applied forces. See, if you want to write a free body diagram for a system, then that free body diagram should represent only three forces, only three things. The first one will be the self weight of the body. The second one will be the reaction which is offered from the object. The third one is the applied forces. Only these three things should be there in the free body diagram for a system, and always this will be the first step in order to solve any problem in the equilibrium of forces. In order to explain this concept, I am going to consider an example. See, there is a ball which is resting on a floor. The ball is resting on a floor. Resting on a floor. Right? I am going to apply a force on the ball and the magnitude of the force is capital P, and this is the center of the ball, which is O. This is a system, right? In this system, there is a ball and ball is resting on the floor, and I am going to apply a force on this ball. If we want to write a free body diagram for this particular figure, for this particular system, then the free body diagram should represent the self weight of the ball. Then the free body diagram should represent the reaction which is offered by the floor. Then I need to represent the applied force P. Right? In the free body diagram, see, this is the ball, this is the center of the ball, and that is O. Now I am going to represent the self weight of the ball. The self weight of the ball should be represented in vertically downward direction. Let me call it as W, that is the self weight of the ball. Always the self weight of any object will be vertically downwards because of the gravitational force, because of the gravitational attraction. That is the reason why I have represented the self weight of the ball which is acting vertically downwards, and always the self weight of any object will be passing from its center. Right? Next I am going to represent the reaction which is offered by the floor on the ball. See, the ball is resting on the floor, right? The floor should offer equal reaction on the ball. That is the reason why the ball is stable. If the floor will not exert any reaction, then the ball will sink into the floor by its self weight. If the ball should be stable, if the ball should be resting here and if the ball should be stable, the floor should offer equal reaction on the ball. Now I am going to represent the reaction which is offered by the floor on the ball, and always it will be vertically upwards, and this will be the reaction which is offered by the floor on the ball. That is the reason why this particular ball is resting on the floor stably without sinking. And that is the next, that is the one more force, that is the reaction offered by the floor. Next I need to represent the force, the applied force, that is the P. The line of action of the applied force should be to the center of the body. The line of action of the reaction offered by the floor should be towards the center of the body, and this will be the free body diagram. Even this free body diagram can be represented like this. See, this is the point O and this is W, that is self weight. This is the reaction, that is R, and this is the applied load P. See, this free body diagram is representing the self weight of the ball, reaction which is offered by the floor, and this is the P, that is the applied forces. That what I said here. See, free body diagram is the isolated diagram which represent the self weight of the body, reaction, and the applied forces. For this particular system, this is the free body diagram, and always all the forces line of action should be passing from the center of the body. Understood? Let us consider one more example. I am going to consider a ladder which is resting on the floor and the wall. So this is the ladder, and the ladder is resting, it is taking the support at the floor and it is taking the support of the wall, right? Now let me apply a force here, that is 600 Newton is the external force, right? Now let me apply one more force here of 100 Newton. So 100 Newton and 600 Newton, these two forces are the applied forces, right? Now let us draw the free body diagram for this system, right? The free body diagram should represent the self weight of the ladder, the reaction offered by the floor, and the reaction offered by the wall, and then I need to represent the applied forces, right? See, the free body diagram for the ladder, always the self weight of any object will be passing from the center of the object, right? And always it will be vertically downwards due to the gravitational attraction. So this will be the self weight of the ladder. Next, I am going to represent the external or the applied force, that is 600 Newton, and then this will be 100 Newton. These are the applied forces. Now I am going to represent the reaction which is offered by the floor, and let me represent like this, which is vertically upwards, and it is R1. Now the reaction which is offered by the wall at this particular point, and the reaction will be horizontal and it will look like this. Let me call it as R2. R1 and R2 are the reactions which is offered by the floor and by the wall on the ladder. That is the reason why ladder is not sliding, it is stable, because of the reaction which is offered by the floor and by the wall. That is most important. If there was no reaction from the wall and the floor, the ladder cannot be used. It will slide easily when you climb the ladder, right? So this is the free body diagram for this particular figure. That means if you want to write the free body diagram for any particular system, then the free body diagram should represent at last the free body diagram should represent the self weight of the object. The second one is the reaction offered by the other objects. Then last one, it will be the applied forces. Got it? Next, let us move to the next concept, and that is types of forces. Let us move to the next concept, and that is types of forces acting on the body. See, consider any system. If you consider any system, there will be only two types of forces. The first one is the applied force. The second one is the non-applied force. There will be only two types of forces will be acting on one particular system. So in order to explain this, I am going to consider an example. See, this is the body, same example, which is resting on the floor, and I am going to apply a force P and then a force Q, and this will be the center of the object O. This is one particular system, right? Applied forces is nothing but if you are going to apply an external force on the body, then that force is called as the applied force. And always the applied force will be having a contact point on the body. See, P is having a contact point at this particular point. So P is having a contact point on the body, and Q is also having a contact point on the body. So I can say P and Q is the applied forces because I am externally applying the forces on that particular body. Right? The second one, it is called as the applied forces and non-applied forces. In non-applied forces, this is self-weight and this is the reaction. Right? Self-weight of the object can be represented vertically downwards, and it should pass from the center of the object, and this will be the self-weight W. And the next non-applied forces is the reaction which is offered by the object. The floor is going to offer the reaction on the ball, and this is the reaction on the, that is the reaction R. So W, self-weight, and the reaction are called as non-applied forces. P and Q are called as the applied forces. A very simple concept, and this concept will be very useful in order to solve the problem, so that you can know which are the applied forces and which are the non-applied forces. Right? So with this, I am going to end this session. So in the next session, I am going to start the problems. Okay? Thank you.